Welcome back to the deep dive. We're shifting gears today. Usually we take a topic and give you the executive summary, the cocktail party version. But today we are doing the exact opposite. We are initiating what the documentation refers to as Project Ampere.
It's a fitting name. It sounds a bit like a covert operation, honestly. But in reality, it's a rigorous back-to-basics, but I should say advanced basics reconstruction of avionics fundamentals.
Exactly. We have a massive extraction inventory sitting in front of us, primarily sourced from the NCT AET certification course material. That's out of the University of Arkansas Pulaski Technical College, plus some incredibly dense supplementary texts on military standards and circuit physics.
And the premise of this deep dive is highly specific. We aren't here to teach you what a battery is. If you're listening to this, we assume you already know a battery stores chemical energy.
Right. We assume you know the vocabulary. You know what a resistor does, you know what a capacitor is. But the gap we are bridging today, the actual Project Ampere mission, is the gap between knowing the textbook definition of a component and understanding its physical behavior at 40,000 feet.
Under heavy load, after 5,000 flight cycles.
Exactly. That is the key distinction. We're moving from the classroom definition straight to the flight line reality. The source material emphasizes this repeatedly. In aviation, precision is the only safety margin.
It really is.
So we're going to deconstruct the aircraft's DC electrical system down to the atomic level, literally looking at electron shells. And then we'll build it back up to the complex line replaceable units, the LRUs, that you find in ATA chapters 24 and 34.
And we're going to do this by treating you, the listener, as a peer. A master technician or an aerospace engineer who just needs to refresh their first principle thinking. Because, as we both know, when a 787 throws a massive cascade of errors on the AIK's display, the manual tells you what box to swap. It absolutely does not tell you why it failed.
No, it doesn't.
And understanding why the actual physics of the failure is what separates a parts changer from a true elite troubleshooter.
So let's get right into it. Section 1. The quantum foundation. The source material starts deep, subatomic deep. We are looking at the fundamental structure of matter, specifically conductors, and the absolute protagonist of this story is copper, atomic number 29.
It is the gold standard, ironically, for a reason. But to really understand why, we have to look at the electron configuration provided in the data. It's argon core, 3d10, 4s1.
Right.
Now, for those who haven't stared at a periodic table since university, that notation is just the physical map of where the electrons live. The core is stable, like the noble gas argon. The third shell is totally full with those 10 d-block electrons, but then you have that fourth shell.
The force one.
Yeah.
Just one solitary electron sitting way out in the nosebleed section.
Right.
Incredibly far away from the positive pole of the nucleus.
Exactly. That is the valence electron. In a solid block of copper, the atomic structure forms a crystal lattice. Because that fourth shell electron is so physically distant from the nucleus, it is very loosely held. But here is the actual deep dive aspect that the text highlights. It's not just about distance, it's about energy bands.
The valence band versus the conduction band. Let's unpack that.
Right. In an insulator, like the Teflon or Kapton wrapping around an airframe wire, there is a massive energy gap between where the electrons currently reside, the valence band, and where they need to be to actually move and carry current, which is the conduction band.
You'd need to apply a lethal amount of voltage to force those electrons to jump that physical gap.
Which is exactly why you don't get electrocuted touching the insulation. But in copper,
those bands literally overlap.
They do. The gap is effectively 0 electron volts. The valence band and the conduction band share the exact same space, so that single 4s1 electron requires 0 extra energy to drift. Just the ambient thermal energy from room temperature is enough to knock it away from its parent atom and into what we call the electron sea.
It instantly becomes a free electron.
Precisely. And that is why copper is the king of avionics. It's not just that it conducts, with almost 0 persuasion. Now, a question I see a lot, and the source material actually alludes to this anomaly, is about silver and gold.
Yeah, because silver is technically a better conductor than copper.
Yeah.
It has a lower fundamental resistivity. So why aren't we wiring commercial jets with silver? Cost has to be the primary driver.
Yeah, cost is a huge factor, sure. But technically, from an engineering standpoint, there's a fatal flaw. Silver reacts aggressively with oxygen and sulfur in the environment. It tarnishes. And that black tarnish is silver sulfide, which is an incredibly poor conductor.
Oh, wow.
Yeah, so in a high vibration, high moisture, rapid temperature cycling environment like a commercial airframe, that corrosion profile is a complete nightmare. Copper corrodes too, obviously, but copper oxide is structurally stable and much easier to manage.
And what about gold? Because we see gold plating on connector pins and avionics bays all the time.
Gold is fascinating. It's a noble metal, so it absolutely does not corrode, but physically, it's incredibly soft. If you drew a 20-gauge wire out of pure gold, it would stretch, sag, and snap under the basic G-forces of a standard climb-out. Plus, it's actually less conductive than copper.
So we use gold strictly for the contact surfaces.
Exactly, where we need a completely oxidation-free mating surface. But we use copper for the transport phase, where we need mechanical strength and low resistance over long runs.
That makes perfect sense. Now let's pivot to the other side of this atomic coin, the magic numbers of valency. The source data is very clear here. 1 to 3 valence electrons means you have a conductor. 5 to 8 means you have an insulator. But the number 4, that's the absolute game changer for modern aviation.
Silicon and germanium, the tetravalent elements. They have exactly 4 valence electrons. They are sitting right on the fence. They aren't conductors, and they aren't true insulators. They are semiconductors.
And this introduces the concept of the forbidden gap.
Yes. Unlike copper with its overlapping bands, silicon has a distinct gap. It's about 1.1 electron volts. At absolute zero, a pure silicon crystal is a perfect insulator. Nothing moves, period. But 1.1 eV is a jumpable distance if you apply a specific controlled amount of energy. This characteristic is the foundation of literally all modern avionics logic.
But pure silicon is functionally useless for us out of the ground.
Right.
We have to modify the crystal lattice.
We have to dope it. And we're talking about controlled alloying here.
Yeah.
We take a pure silicon crystal and we inject specific impurities. If we inject a pentavalent material, an element with 5 valence electrons, like antimony, 4 of those electrons bond covalently with the silicon structure. But that 5th one...
It has absolutely nowhere to dock.
Right. It's structurally orphaned. It becomes a permanent free electron.
So by doing that, we've manufactured N-type material,
Yeah.
a negative charge carrier.
Correct. And conversely, if we inject a trivalent material, something with only 3 valence electrons, like boron, we create a structural deficit in the lattice. We have an empty parking spot, a hole. This creates P-type material.
So why does a line technician troubleshooting a landing gear control unit at 2 in the morning need to care about crystal lattices, holes, and free electrons? Let's ground this in reality.
They need to care because when you physically sandwich P-type and N-type materials together in a factory, you create a PN junction. And that junction instantly forms a built-in barrier potential. For silicon, that barrier is roughly a 0.6 to 0.7 volts. That is the toll you have to pay to get any current to flow across that junction.
And this right here is the critical aha moment for diagnostics. The source material drives this home. If you are measuring a diode or a bipolar junction transistor in a circuit,
and you do not see that 0.7 volt drop across the junction, with absolute certainty the component is structurally compromised. If you measure 0 volts across it, it's shorted. The toll booth has been smashed to pieces. If you measure the full source voltage across it, it's completely open. The bridge is gone.
that 0.7 volt number isn't just trivia you memorize for the NZATT exam. It is the vital sign of the component. It's the physical, measurable manifestation of that 1.1 EV forbidden gap we just discussed.
Exactly. And this leads us naturally into a massive conceptual error that the Avitech source material goes out of its way to correct, the water pipe analogy.
Oh yeah. We all learned basic electricity by imagining water flowing through a plumbing system. Voltage is the water pressure, current is the flow rate, resistance is a pinched pipe.
It's an incredibly useful heuristic for a first-year apprentice. But for a master technician working on advanced systems, it is actively dangerous. The model completely falls apart when you start dealing with high-speed avionics, things like ARN-C429 data buses or AFDX Ethernet systems.
Because the source makes a very hard distinction between electron drift and signal speed. We need to break that down.
Let's use a mechanical analogy that actually works. Picture a completely full tube of marbles. That tube is your copper wire. The marbles are the individual electrons. If I forcefully push one extra marble in the left end, a different marble pops out the right end almost instantaneously.
Right. The physical transfer of energy, the pop, happens in a microsecond.
That energy transfer is the signal speed. It actually travels as an electromagnetic wave outside the physical wire, guided by the conductor, at a significant fraction of the speed of light.
But the specific marble you pushed in on the left,
that individual marble, the single electron, is barely moving at all. It's bouncing around in the lattice, colliding with copper atoms, drifting forward at a microscopic pace. We're talking millimeters per hour. That is electron drift velocity.
So why is this specific distinction so vital for a technician operating under the Project Ampere mindset?
Because if you truly believe electricity is just water flowing through a pipe, you remain completely blind to the concept of impedance. When we send a high-frequency digital signal down a twisted pair wire, we aren't just pushing marbles, we are propagating a complex electromagnetic wave. If that wave hits a connector, where the physical characteristics of the wire suddenly change, say a slightly crushed dielectric, a bad crimp, or a microscopically corroded pin, some of that wave energy physically bounces back.
Signal reflections.
Exactly, standing wave ratio issues. The water plumbing analogy cannot explain reflections. Water doesn't bounce back down a pipe just because the pipe got slightly wider, but wave theory explains it perfectly. If you have impedance mismatches in a flight-critical data bus, that high-speed signal bounces back and literally collides with the next incoming data packet.
So the flight computer at the receiving end doesn't see a clean binary 1 or 0.
No, it sees garbage. It sees data collisions and cyclic redundancy errors.
Which means a technician who is just using a standard ohmmeter to look for a clogged pipe, looking for basic DC continuity, is hunting for the wrong physics entirely. They need to be looking for impedance mismatches, changes in the stiffness of the medium.
Precisely. That is exactly why we diagnose coaxial and data cables with time-domain reflectometers, the TDRs. We aren't checking if the wire is whole, we are pinging the wire to see exactly where the wave bounces back. We are looking for the acoustic echoes of a bad crimp.
Let's transition into section 2 of the outline, the laws of the land. We're getting into circuit physics and math. The source material highlights Ohm's law, but it explicitly avoids the basic V equals I times R. It goes straight to the material science formula for resistance. R equals rho times length divided by area.
Yes, this is the structural formula for the conductor itself, and it introduces a variable that quietly kills more electromechanical components than almost anything else on the airframe: temperature.
Temperature coefficient.
Right. Most of the primary conductors we use in aviation, specifically copper and aluminum, possess a positive temperature coefficient, which means as the ambient or operating temperature rises, their physical resistance increases.
Let's contextualize this with the scenario provided in the outline. An aircraft landing gear motor. Let's build this out.
Yeah.
You have a heavy regional jet operating in the summer. The landing gear retraction is being reported as sluggish, but the pilot says it only happens on the 3rd or 4th flight of the day. Never the first. So the plane gets to the hangar the next morning, you troubleshoot it, it works flawlessly. The transit times are perfect.
It's the classic diagnostic trap. In the morning, the aircraft is cold-soaked. The massive copper windings inside that retraction motor are sitting at ambient temperature, maybe 20 degrees Celsius. You put your millimeter on the coils, and the resistance perfectly matches the maintenance manual. You run the gear, the current draw is nominal, so you sign it off. No fault found. Return to service.
But the pilot inevitably writes it up again the next afternoon.
Because on that 3rd flight of the day, that motor has been working hard. And crucially, it's sitting inside a closed wheel well that might be adjacent to a brutally hot carbon brake assembly or a bunch of hot hydraulic lines. The copper mass in those motor windings has now heat-stoked to something like 100 degrees Celsius.
So what does the rho formula tell the master technician here?
Since copper has a positive alpha, the resistance of those windings has increased significantly from the morning baseline. It's simple Ohm's law from there. If resistance goes up and the aircraft bus voltage is fixed at 28 volts, the total current flow drops.
But a DC motor fundamentally relies on current to generate magnetic torque.
Exactly. Torque is directly mathematically proportional to armature current. So the hot motor has a higher internal resistance, which means it physically cannot draw enough current, which means it produces significantly less torque. It actively struggles to lift the heavy gear assembly against the aerodynamic slipstream. It gets sluggish. In a worst-case scenario, the motor might actually stall out completely.
And if it stalls?
Then you trigger a completely different failure mode. A stalled electric motor looks exactly like a dead short to the electrical bus because there's no counter EMF being generated by rotation. But we'll unpack counter EMF in the magnetism section. The core takeaway here is this. If you, as a diagnostician, do not account for the thermal shift in baseline resistance, you are chasing ghosts. You have to intellectually simulate the failure conditions. You either physically heat the component, or you run the math to calculate the expected resistance shift at operating temperature and see if it falls out of the operational tolerance.
That is exactly the masterclass approach we are talking about. It's never just a question of is it broken? It's a question of is it broken under these precise thermal and environmental conditions?
Exactly.
Let's look at Kirchhoff's laws next. KCL and KVL. These are usually taught as completely abstract textbook puzzles, but the Project Ampere data reclassifies them as diagnostic logic.
KCL, Kirchhoff's current law, is arguably my favorite conceptual tool for hunting down phantom loads. The physical law is elegantly simple. The algebraic sum of all currents entering a node must exactly equal the sum of all currents leaving that node. Electrons do not just evaporate into the ether.
So imagine a primary 28-volt DC bus. You have exactly 50 amps flowing out of the transformer rectifier unit, the TRU. You look at your load analysis sheet, you add up the lights, the navigation, the comms, the boost pumps, and you calculate that the active systems should only be drawing 48 amps total.
But the digital ammeter on the TRU clearly says 50 amps. You have 2 solid amps of current completely unaccounted for. Where are they going? KCL dictates they must be going somewhere. They are flowing back to the source.
And usually that somewhere is a place you really do not want current to be.
Without a doubt. It could be carbon tracking across a dirty phenolic terminal block, slowly leaking to the airframe. It could be a slightly frayed Teflon wire jacket vibrating against a hydraulic return line, creating a high resistance path straight to ground. It's not a dead short, it's not pulling enough amperage to pop a thermal breaker, but it is a constant leak. And that 2 amps is actively generating heat somewhere hidden in the airframe. That is a latent fire hazard. KCL is the mental framework that tells you to stop looking at the documented loads you know about and start hunting for the parasitic leak you don't.
Then we have KVL, Kirchhoff's voltage law. The rule that the sum of all voltage drops in a closed loop must perfectly equal the source voltage. The specific Project Ampere diagnostic tip here is regarding the open resistor scenario.
This one is the absolute smoking gun of avionics troubleshooting. Let's say you have a basic series circuit, a string of incandescent cockpit subpanel lights. The whole string is dead. You grab your digital multimeter, you click the black ground lead to the airframe chassis, you take the red probe and touch the terminal immediately before the first bulb in the series. The meter reads 28 volts. Good, power is getting there. You probe the terminal immediately after the first bulb. The meter still reads 28 volts.
Wait, hold on. If that first bulb was functioning normally, you should see a measurable voltage drop across its filament.
You absolutely should. But remember Ohm's law, V equals I times R. Since no current is flowing through the series circuit because there's a physical break somewhere downstream, the I value is 0. 0 times any resistance is 0. So there is 0 voltage drop across that good bulb. The electrical potential simply floats all the way past it.
So you keep leapfrogging your probe down the line. 28 volts, 28 volts, 28 volts. And then suddenly, across one specific connection, you read 0 volts.
You found the break. The physical discontinuity is exactly between the last place you measured 28 volts and the first place you measured 0. The entire source voltage of the system will appear directly across the open, broken component. If you put your meter leads across a single component in a 28-volt system and you read a full 28 volts drop across it, that component is open, it has infinite resistance, it is physically holding back the entire electrical pressure of the aircraft.
It's so counterintuitive for junior mechanics. They probe across a component, see 28 volts, and think, oh great, it has full power. No, it has maximum potential, but it has 0 flow. It is acting as a dam, not a river.
Exactly. A functioning resistive component in a closed loop should only ever drop a calculated fraction of the total voltage. If it drops all of it, it's the point of failure. KVL proves it.
Let's push into section 3, component intelligence. We are moving from physics into hardware, looking at components through the lens of strict mil-spec standards. Let's start with the humble resistors, specifically the mil-PRF 55342 standard. We just talked about heat crippling a copper motor winding. How does temperature affect precision resistors inside navigation computers?
This is a massive issue for ATA Chapter 34, the navigation systems. Think about a VOR receiver or an instrument landing system, the ILS. These analog to digital systems rely on incredibly precise internal voltage dividers to accurately interpret microvolt radio signals from the ground. If the internal resistance values of those dividers drift even slightly, the mathematical calculation of the aircraft's position drifts with it.
And the thermal environment an aircraft operates in is absolutely brutal.
It's extreme. A commercial jet sitting on the tarmac in Dubai in August might have an avionics bay heat soaking at plus 50 degrees Celsius. 20 minutes later, after a steep climb, the aircraft is at 30,000 feet, blasting through freezing temperatures. At cruise altitude, it's structurally soaked at minus 55 degrees Celsius. That is a 105 degrees Celsius temperature swing in less than half an hour.
If a manufacturer tried to use a cheap consumer-grade carbon film resistor from a hobby shop,
Its internal resistance might fluctuate by 5, maybe even 10% over that extreme thermal gradient. That is its temperature coefficient of resistance, its TCR. If your critical reference voltage shifts by 10%, your ILS localizer needle might boldly show you perfectly centered on the runway, when in physical reality, you are drifting 300 feet into the grass at 140 knots.
So a mil-spec resistor is explicitly engineered to remain chemically and electrically rigid.
We specify thin film surface mount resistors with a TCR of something like 25 parts per million per degree Celsius. They are chemically monolithic. It guarantees that mathematical center remains physical center, regardless of whether the aircraft is baking on a desert ramp or deep freezing in the stratosphere.
That is a brilliant translation of the standard. Next up in the outline, capacitors. The governing physics formula here is W equals 0.5 times C times V squared. Energy stored in joules equals 1/2 the capacitance times the voltage squared.
The squared variable in that equation is the killer. I mean that literally. It means the energy storage relationship is entirely quadratic. If you double the charge voltage on a capacitor, you don't just double the stored energy, you quadruple it. If you triple the voltage, you are holding 9 times the kinetic energy.
The primary application the source provides for this is ATA33, aircraft lighting. Specifically, the high-intensity discharge anti-collision strobes.
Right. Xenon flash tubes. To generate that blinding, distinct white flash that makes a 737 visible through clouds from 20 miles away, you have to dump a staggering amount of electrical energy into the xenon gas in a matter of microseconds. You cannot pull that kind of instantaneous transient current directly from the aircraft battery. The internal chemistry is far too slow. So we utilize a massive capacitor bank inside the strobe power supply. We slowly trickle charge it up to 400 or 500 volts.
And when the trigger circuit fires,
it violently dumps all those stored joules across the gas tube instantly. But here is the critical safety protocol that the Project Ampere syllabus insists we cover. That capacitor bank retains that lethal charge, even if the aircraft master switch is physically turned off, even if the main battery is completely removed from the airframe.
it is a high-voltage trap just waiting for an uninformed technician's hand.
If you open that power supply and accidentally bridge those terminals with your bare hand, your body completes the circuit. That quadrupled V-squared energy immediately discharges straight through your cardiovascular system.
So walk us through the actual master technician way to render this safe. Because I know you don't just grab a massive flathead screwdriver and short the terminals out, right?
No, never do that. If you bridge a 500-volt charged capacitor with a screwdriver, you pull an instant arc. You vaporize the metal tip of the tool, you pit the terminals, and the acoustic shock wave from the spark can actually shatter the internal dielectric of the capacitor or blind you with UV light. You must use a bleeder probe. We call it a chicken stick on the floor. It's an insulated probe with a high-wattage, high-ohm resistor built directly into the handle. You hold it across the terminals, and it bleeds the kinetic energy off safely and slowly over maybe 5 or 10 seconds. It converts the joules into mild heat rather than a plasma explosion.
Always respect the V-squared.
Yeah.
Let's move to transistors. The classic JTX2N2222A. We see this exact part schematic everywhere. But the source material details a fascinating packaging war between the legacy TO18 and the modern SOT23 packages.
The TO18 is the classic metal can package. It literally looks like a tiny silver top hat with 3 gold wire legs sticking out. It's vintage, it's mechanically robust, it's hermetically sealed. The SOT23 is the modern surface mount device, the tiny, flat, black plastic rectangle you see on every modern motherboard.
Let's focus on the TO18 first. The data indicates a very specific and highly dangerous installation hazard involving the metal case itself.
Yes. In many TO18 NPM transistors, the physical metal case is internally electrically bonded directly to the collector pin. This is an intentional design choice to aid in thermal dissipation. The entire metal hat acts as a tiny radiator. But if a technician mounts that transistor through a drilled hole in a grounded aluminum chassis,
And the bare metal case physically touches the aluminum.
you have just created a dead short from the collector circuit directly to airframe ground. If that collector was actively switching a 28-volt load, you instantly have a catastrophic direct short. The magic smoke comes out immediately.
So how is this safely engineered in practice?
You are required to install a mica washer. It is a microscopic, completely transparent disc made of crushed mica mineral. It seats exactly between the base of the transistor and the metal chassis. Mica is incredibly unique because it readily conducts thermal heat, allowing the transistor to utilize the chassis as a heat sink, but it perfectly insulates electrical current. You also have to use a tiny nylon sleeve over the mounting screws so the threads don't short the case.
I can vividly see a rushed third shift technician dropping that washer, not finding it, and thinking, it's just a little piece of clear plastic, the transistor physically bolted down, it's fine.
And the absolute second they close the breaker, the circuit violently destroys itself. It is the quintessential invisible part failure.
Conversely, the SOT23 surface mount chip doesn't have a metal case to short out, but it has a completely different structural enemy: high-frequency vibration.
Right. It has no flexible wire legs to act as shock absorbers. It is soldered, completely rigid, flat against the fiberglass board. In a severe vibration zone, for example, inside an engine electronic control, an EEC, bolted directly to the cold section of a turbofan engine, the actual circuit board microflexes constantly. But the solid plastic SOT23 chip cannot flex, so all that mechanical stress transfers directly to the solder joints, and they eventually crack.
Solder fatigue.
Exactly. Microscopic stress fractures in the joint. That is precisely why we demand JAN-TSV certified parts for those severe operating environments.
Let's decode that alphabet soup right now.
Yeah.
JAN-TX, JAN-TXV, JAN-S. This is the MIL STD 19500 hierarchy for discrete semiconductors.
JAN simply stands for Joint Army-Navy. It's the baseline qualification. It guarantees good material quality of vetted manufacturing lines, but it only mandates statistical batch testing.
So what upgrades a part to JAN-TX?
The X stands for Testing Extra. This is the absolute workhorse standard of commercial aviation. Every single component in a JAN-TX lot undergoes a 100% burn-in process. The factory places every individual transistor into an oven, powers it up to its maximum rated voltage and current, and leaves it running continuously for usually 48 to 96 hours before it ever ships. The engineering logic here is to force infant mortality. If a silicon wafer has a latent microscopic defect, thermal stress will usually cause it to fail very early in its operational life. We want to force that failure while the part is sitting in a test fixture in the factory, not while it's actively driving a relay in a flight management computer over the Atlantic.
And JAN-TXV takes it a step further.
The V stands for visual. Before the factory seals the metal or plastic package, a highly trained human inspector, or increasingly, a high-resolution machine vision system, physically inspects the bare silicon die under a microscope. They verify the microscopic gold wire bonds. Are they perfectly straight? Is the die perfectly centered on the substrate? They are actively hunting for structural physical defects that standard electrical burn-in testing might not catch. This is a non-negotiable requirement for fly-by-wire and primary mission-critical hardware.
And the absolute top tier, JAN's space grade.
Primarily used in low Earth orbit satellites, obviously, but increasingly mandated in extreme high-altitude aircraft. The U-2, the Global Hawk, and even commercial wide-bodies like the 787. The primary engineering concern driving the JANS standard is radiation hardening.
This connects perfectly to Section 6 of the outline, but let's attack it now while we are discussing the silicon. Why does a tiny solid-state transistor care about atmospheric radiation?
Because high-energy atomic particles, cosmic rays, solar flares, high-energy neutrons easily punch through the thin atmosphere at 40 or 50,000 feet. When one of these high-energy particles physically impacts a silicon chip, it violently ionizes the atomic lattice structure. It literally leaves behind a microscopic wake of displaced electrical charge. Over thousands of flight hours, this total ionizing dose, the TID, permanently accumulates inside the delicate oxide layers of the transistor.
And that trapped charge physically alters how the transistor operates.
It permanently shifts the threshold voltage, the VDIF. A logic transistor that was precisely designed to turn on at exactly 0.7 volts might slowly drift over 5 years to 0.5 volts or require 1.0 volts. Eventually, the timing of the logic gate completely breaks down. It stops switching correctly. Or worse, a single massive high-energy particle can cause a single event effect. And C, it injects so much instant charge that it causes a spontaneous bit flip in a memory register. A critical binary 0 spontaneously becomes a 1.
And suddenly, the autopilot computer interprets a bank left command as a hard bank right.
Exactly. It's a soft error, but the consequences are catastrophic. That is why JANS components utilize exotic manufacturing techniques like silicon on insulator, SOI technology. They physically manufacture the transistor on top of an insulating layer of glass to drastically reduce the total volume of silicon where that parasitic charge can collect. It is astronomically expensive, but it perfectly insulates the logic states from the high-altitude radiation environment.
Incredible. Let's shift to Section 4, Magnetism, induction, and power. The source material frames this around the dynamic duo of electromagnetism, Faraday and Lenz.
You absolutely cannot teach one without the other. They are completely symbiotic. Faraday's law is the raw engine. It states that if you physically move a conductor through a magnetic field, or more accurately, if you change the total magnetic flux over a given period of time, you induce a voltage in that conductor. That is the fundamental physics of how every generator and alternator on the aircraft creates power.
But Lenz's law immediately steps in and says, not so fast.
Lenz's law is the universal law of absolute opposition. It dictates that the newly induced current will instantly create its own magnetic field. And crucially, that new magnetic field will violently fight the exact physical motion that created it. It is pure magnetic friction.
Let's apply this directly to a heavy DC motor on the airframe. We play 28 volts, the armature starts spinning. Why does Lenz matter here?
Because as that motor armature spins faster and faster, its copper windings are actively cutting through the internal stationary magnetic field. So, based on Faraday's law, the motor is essentially acting as a generator at the exact same time it is functioning as a motor. It physically generates a reverse voltage that actively pushes back against the incoming 28-volt supply from the aircraft. We call this phenomenon counter EMF.
And this is actually a highly beneficial characteristic, right?
It is the only thing keeping the motor from destroying itself. This counter EMF is what actively limits the continuous current draw. When a motor is spinning at its designed high speed, the counter EMF is extremely high, nearly matching the supply voltage. So the net current flowing into the motor drops to a very safe, low sustaining level.
But what physically happens if that motor stalls? Let's go back to our landing gear scenario.
Yeah.
Say the physical gear mechanism completely jams on a broken up block.
The motor armature is physically locked. It stops spinning completely. If it stops spinning, there is zero relative motion between the coils and the magnetic field. Zero Faraday effect, which means absolute zero counter EMF.
So the only physical property limiting the incoming electrical current is the raw DC resistance of the copper wire itself.
Exactly. And as we established, the resistance of heavy-gauge copper motor windings is incredibly low, fractions of an ohm. So without that protective counter EMF pushing back, the current instantly spikes to a massive destructive value. We call it locked rotor current.
And that massive thermal spike is what violently pops the circuit breaker.
Yeah.
Or if the breaker fails to clear, it physically melts the motor windings.
Yes. The innate protection of Lenz's law completely vanishes the millisecond the physical motion stops. This is a vital diagnostic concept for technicians working on heavy actuators. If a 50-amp motor breaker pops the instant you throw the switch, you have to ask yourself a mechanical question before an electrical one. Is the motor internally shorted to ground, or is the attached mechanism simply jammed tight, preventing the counter EMF from forming?
Brilliant. Now we are getting into the heart of the deep dive. Section 5, the art of troubleshooting. The source calls this the NZAT stress test. We have 3 distinct diagnostic scenarios here. I want to actively role-play these. I'll lay out the physical evidence on the flight line, and you walk us through the exact Sherlock Holmes logic tree.
I love these. Let's do it.
Scenario 1. The parallel short. You are diagnosing a passenger audio entertainment bus. You have 3 300-ohm speakers wired perfectly in parallel. Suddenly, the primary circuit breaker pops. A line tech resets it, which we strictly know they shouldn't do without investigating, but they do, and the breaker instantly pops again with an audible snap and a flash.
Okay. Step 1, define the architecture. In a parallel circuit, voltage is the constant across all branches. Each of those 3 speakers is seeing the full 28 volts.
Right. And through wear and tear, one of those speakers has developed a hard, direct internal short across its voice coil.
Let's run the math. Speaker A remains 300 ohms. Speaker B remains 300 ohms. But speaker C has collapsed to 0 ohms.
Physics time. What happens to the current?
The common colloquialism is that current follows the path of least resistance, but that's technically incomplete. Current flows through all available paths simultaneously in exact proportion to their conductance. Let's look at the current through the shorted branch, speaker C. I equals V divided by R. I equals 28 volts divided by 0 ohms.
Which mathematically approaches infinity.
Exactly. In the physical reality of the aircraft, it pulls hundreds or thousands of amps, limited only by the total capacity of the generator and the melt point of the copper wire. The vast, overwhelming majority of the current aggressively rushes through that single 0 ohm branch. The total effective resistance of the entire parallel network instantly collapses to near zero.
And what happens to the audio and the other two healthy speakers?
They are completely starved. They don't matter anymore. The entire parallel bus is violently dragged down by the absolute weakest link. The massive instantaneous current spike flowing through the bus tie trips the bimetallic thermal element inside the breaker in milliseconds.
So the critical takeaway for the tech on the floor. A single shorted component on a parallel bus takes down the entire bus architecture. You cannot troubleshoot it as a whole.
Correct. You have to physically isolate them, unplug the branches one by one, measure the resistance of each unit independently, and find the specific one reading zero.
Let's move to scenario 2. The transistor switch. This is a pure logic puzzle. You are deeply probing a printed circuit board, troubleshooting a solid-state relay driver. You have an NPN transistor actively acting as a ground switch for a mechanical relay coil. You put your meter on the base emitter junction, the VB, and you read a steady 0.7 volts.
Okay, stop right there. That 0.7 volt reading is the active turn-on command from the processor. The transistor junction is successfully forward biased. The logic computer is screaming at that transistor to turn fully on and conduct current.
Okay, then you move your probe to measure the collector voltage relative to ground, the VCC. Since the transistor switch is commanded closed, you fully expect the voltage to be pulled low to saturation, almost 0 volts.
Yeah.
But instead, your meter reads a solid 28 volts sitting right on the collector pin.
This is a beautiful, classic failure signature. Let's trace the logic. You have a verified active input command, 0.7 volts at the base, but the output response at the collector is completely wrong. It is sitting completely high at the source voltage of 28 volts.
What exactly does that physical state mean?
Let's visualize the circuit. The 28-volt source goes through the relay coil, then hits the collector pin of the transistor, and the emitter pin goes to ground. If that transistor switch was successfully turned on by the base signal, it would create a near-zero ohm path to ground. It would forcefully pull that collector voltage down to roughly 0.2 volts, sinking the current and energizing the relay.
Right. It aggressively connects the bottom of the coil to the ground plane.
But since the measured voltage is not being pulled down, it is hovering high at 28 volts, it proves that the internal silicon switch is completely broken. The solid-state path is physically severed. The transistor has failed open.
So the diagnostic mantra is input command present, output state absent equals failed open.
Precisely. Now contrast that. If the transistor had failed completely shorted, internally melted, the collector pin would read near 0 volts continuously, completely ignoring the base signal. The relay would be stuck permanently energized even if you unplugged the flight computer.
That is fantastic logic. Scenario 3, the fuse paradox. This one is mechanically simple, but it dictates a very specific response protocol. An inline glass fuse blows, the tech pulls it, visually confirms the element is broken, and inserts a perfectly matched replacement. They toggle my master power switch back on, and instantly, SNAP. The new fuse detonates. 0 delay.
The absolute immediacy of that snap is the critical data point here. You have to understand how fuses operate physically. They are thermal devices. Electrical current flows through the zinc or silver element, generates I²R heat, and literally melts the metal to break the circuit.
Right, so if it's a slow creeping overload, let's say a flat motor with degrading dry bearings drawing slightly too much current, the fuse element might slowly glow for 10 seconds or even a full minute before finally sagging and fading out.
Exactly, it's a thermal lag. But an instantaneous, violent SNAP, often blackening the inside of the glass tube, implies an absolutely massive, unconstrained surge of current. We are talking hundreds of amps in a millisecond. That signature strictly indicates a direct hard short to ground.
Meaning, the primary power feed wire has completely chafed through its insulation and is physically welded to the aluminum airframe.
Yes, near zero resistance, maximum theoretical current. The fuse element instantly vaporizes into plasma before it even has time to glow red. If you witness that exact violent signature, your absolute worst move as a technician is to install a larger amperage fuse just to see if it holds.
Because if you do that,
you bypass the engineered weak point. The fuse will hold, but the copper wire harness buried deep in the fuselage will instantly become the new fuse. It will melt its insulation, ignite the adjacent bundles, and you will start an uncontainable Class Charlie fire inside the aircraft structure. You have a hard physical short. Stop resetting power and go find the completely bare wire.
that is exactly why we do this, bringing the theory directly to the worst-case reality. Finally, let's unpack Section 6. Niche hazards. The outline calls these space-age problems. We already took a deep dive into high-altitude radiation, but we have to discuss the tin whisker menace. Honestly, it sounds like an old pirate myth.
It sounds absurd, but it is an absolute scourge of modern aerospace electronics. The root cause connects directly to the global RoHS initiative, the restriction of hazardous substances. In the early 2000s, the consumer electronics world aggressively pushed to completely eliminate lead from global manufacturing. So the entire industry rapidly transitioned from traditional leaded solder to pure tin plating for component leads.
And we all understand the environmental logic. Lead in groundwater from discarded cell phones is a massive ecological disaster. But why is pure tin such a specific hazard for a closed avionics system?
Because metallurgically, electroplated pure tin is inherently unstable. It holds massive internal compressive stress. To naturally relieve that atomic stress over years, the metal physically extrudes long, incredibly thin, crystalline structures. We call them whiskers. They look exactly like microscopic, perfectly straight hairs growing right out of the metal.
And because they are pure tin, they are highly conductive.
Exactly. And inside a densely packed, modern flight control computer, the pitch between processor pins is a fraction of a millimeter.
Oh, I see where this is going.
Right. That conductive hair silently grows out from one pin, physically bridges the microscopic air gap, touches the adjacent pin, and instantly creates a dead short circuit across the processor logic lines.
But the truly terrifying part of this phenomenon, based on the research docs, is what happens next. Because the whisker is literally thinner than a human hair, its current carrying capacity is almost zero.
Exactly. The absolute instant the short circuit occurs, the raw operating current of the logic board instantly vaporizes the whisker into a puff of microscopic plasma. It acts exactly like an ultra-fast microscopic fuse. It creates a massive logic glitch, forces the flight computer to hard reboot in midair, and then physically destroys all evidence of its own existence.
The ultimate ghost in the machine. A maintenance crew pulls the box, opens the casing, puts the board under a microscope, and sees absolutely nothing wrong.
Zero evidence. The component tests perfectly on the bench, so they sign it off as a transient anomaly. But the underlying stress remains, and another whisker is already growing.
So how does the aviation industry physically defend against this?
We aggressively fight for exemptions from the RoHS mandates. For Class 3 mission-critical avionics guided by IPC JSTD 001, we actively mandate the continued use of traditional leaded solder, SN63 PB37. The physical addition of lead fundamentally alters the crystal matrix of the tin and completely mitigates the compressive stress. Lead completely stops the whiskers from ever forming. Period.
But what if you were forced to use commercial off-the-shelf components that only come with pure tin plating?
Then we rely on conformal coating. After the circuit board is fully assembled and tested, we completely submerge it in a viscous acrylic or silicone polymer. We seal it in plastic. If a tin whisker does manage to spontaneously grow, it immediately hits the dense plastic barrier and structurally buckles. It is a brute force physical shield.
That is fascinating metallurgy. Let's hit the final hazard in the outline. ESD, electrostatic discharge. Everyone in the industry knows they're supposed to wear the blue grounding wrist strap. But the Project Ampere syllabus highlights a shockingly low threshold for catastrophic physical damage. Just 30 volts. I mean, human skin can't even physically perceive a static shock until the potential hits roughly 3,000 volts.
That is exactly the inherent danger. You can walk across a synthetic carpet in the avionics shop, generate 1,000 static volts on your body, pick up a bare printed circuit board, and feel absolutely nothing. No spark, no snap, no physical sensation whatsoever.
But the components on that board.
You just violently discharged 1,000 volts directly into a microprocessor input pin that is physically engineered to handle a maximum of 5 volts. The static arc literally blows a microscopic crater straight through the internal silicon dioxide insulating layer of the chip. You instantly killed the processing core, the board is completely dead, and you don't even know you did it.
And the syllabus highlights a very specific procedural pro tip regarding the wrist strap and test probes. Let's walk through that.
This is a lethal trap for junior techs. You must always physically ground your wrist strap to the chassis ground before you ever touch your oscilloscope probe to the circuit board.
Let's explicitly walk through the human fuse scenario if a tech ignores that rule.
Let's say you are holding a 1,000-volt static charge on your body. You walk up to the bench, you don't plug your wrist strap in, you grab your grounded oscilloscope probe with your bare hand, and you touch the tip directly to an active logic pin on the processor chip.
The charge wants to get to earth ground.
Exactly. And the current path is this. The 1,000 volts flows from your finger, completely bypasses the protective probe casing, enters the logic pin of the chip, blasts through the delicate silicon architecture hunting for a ground path, eventually hits the board's internal ground plane, travels up the ground lead of your test probe, into the massive oscilloscope chassis, and finally dissipates safely into the wall outlet earth ground.
Because you didn't ground your body first, you literally forced the delicate microchip to act as the massive grounding strap for your entire body.
Exactly. You became the high voltage source, and the $2,000 processor chip became the sacrificial victim in the middle of the circuit. Ground your body first, always. It removes the potential difference before you introduce the test equipment.
We have covered an absolutely massive amount of conceptual ground today. From the loose 4s1 electron in a raw copper atom to the intense Janey XV burn-in hierarchy, the deep physics of Lenz's opposing magnetic field, and the hardcore detective work of isolating a parallel short on the flight line.
It is an incredibly dense syllabus, but it all perfectly interconnects. That is the entire philosophy of Project Ampere. The electron fundamentally does not know if it is drifting through a heavy copper battery cable or an exotic space-grade silicon transistor. It merely follows the immutable laws of physics. If you actually internalize those laws on Kirchhoff, Faraday, Lenz, you can accurately troubleshoot literally anything in aerospace. From a simple dome light circuit in a Cessna 172 to a complex phased array radar system on a fighter jet.
Let's wrap this up with the systems view provided in the outro. We look at ATA Chapter 34 systems, things like a Garmin G1000 suite or a Honeywell Primus Apex. To the untrained eye, these are completely impenetrable black boxes.
But they really aren't. They're just complex systems built of these exact simple systems. A Garmin navigation LRU is fundamentally just heavy power supplies using inductors and capacitors, logic arrays built of millions of switching transistors, and precision-resistive voltage dividers reading sensor data. If you truly master the behavior of the individual building blocks, the terrifying black box completely demystifies itself.
The absolute final thought from the source material brings all of this to a point regarding the MEA, the more electric aircraft architecture, aircraft like the Boeing 787.
Right. On legacy aircraft, the line between ATA-24 electrical power and ACA-34 avionics logic was a hard physical boundary. Heavy contactors over here, delicate computers over there. That boundary is now completely gone. We have high-voltage DC networks, 270 volts DC, actively running primary flight control actuators. The delicate solid-state logic computer is directly managing the massive electrical power matrix,
Which amplifies the ultimate risk mentioned in the brief: counterfeit components.
It is the nightmare scenario of modern logistics. If a purchasing agent or a line tech cannot physically spot a counterfeit part, if they don't know what chemical blacktopping looks like on a fake IC chip, they might blindly solder a $2 untested commercial-grade replica chip into a $200 million fly-by-wire aircraft. And because that fake chip never underwent the brutal Jane Tate v. thermal burn-in, it will absolutely fail under stress.
And as the syllabus started, precision is the absolute only safety margin in aviation.
That is the ultimate takeaway. Whether we are discussing the precise torque setting on a terminal lug, the exact parts per million stability of a navigation resistor, or the absolute purity of a doped silicon wafer, uncompromising precision is the physical foundation that keeps us flying safely.
Thank you for joining us on this incredibly deep dive into Project Ampere. It is unyieldingly heavy material, but it is exactly the foundational physics that matters when the manual runs out of answers.
Keep your grounding straps firmly connected.
And make absolutely sure your solder joints stay leaded. We will see you out on the flight line.
Take care, everyone.